share my screen. Hello everyone, welcome to this Proton webinar. I'm Zimo Yang, a second-year graduate student in Professor Wei Xiong's group at UCSD, and I will be the host of today's talk. Before we start, I will make a few announcements about future schedule and mechanism of this webinar series. First, the Journal of Chemical Physics has its special issue of photon chemistry, molecules in cavity and plasmonic media. The editor will be Professor Jason, Shegai, Wei, and Howell, and you are all welcome to contribute. The submission deadline will be October 16th. Our webinar will be held every Wednesday at 9 a.m. Pacific Standard Time, and the registration for each webinar can be made through the link. Here is the future schedule of our future talks. Another thing I would like to mention is that we created this Photon Chemistry online community webpage on Facebook, which allows everyone to share papers and post announcements. You can search by its name. Meanwhile, we have uploaded our recorded videos on this Photon Chemistry webinar YouTube channels. For those who missed the talk, you can subscribe and watch these videos later. Finally, I would like to introduce the mechanism of this webinar. During the talk, attendees are all muted. For those who have questions, you can click this raise hand button and I will interrupt the speaker at an appropriate time and enable your audio to ask questions. Also, you can type in your comments or ideas using the chat function so that you can share a screen. You can share with everyone. For Q&A, we can type your questions here, which will be addressed at the end of the talk. For the questions that are not answered due to limit time, we will collect and send to the speaker after the talk. Now let's move back to this webinar. Today's speaker is Professor Timur Shegai from Chalmers University of Technology. Professor Shegai graduated from Resonant Institute of Science in 2003, and then he moved to Chalmers University of Technology in 2009 as a postdoctor. In 2013, he got into tenure track, and in 2017, he was promoted to faculty associate professor's position. Now, Professor Shegai runs a group focusing on experiments in strong coupling physics, two-dimensional materials, surface-enhanced phenomena such as SERS, quantum and low-temperature plasmonics, and various types of sensing. Their experimental work encompasses single particle molecular microscopy and spectroscopy, angle-resolved and so-called Fourier imaging, nanofabrication, and electron microscopy. Now let's welcome Professor Shegai. Professor, now you may share your screen.
Thank you very much for the introduction. Let me start sharing my screen. So, yeah, I hope you do see it. Yeah, please.
Yeah, no problem.
Okay, thank you very much. So, I would like to start this presentation by thanking the organizers for giving me the opportunity to speak in these complicated times. So thank you for that. In fact, partially motivated by that, today I decided to show some unpublished data simply because we have quite low chances now to meet our colleagues, and I think it will be nice to share with you some new results rather than published stuff which you can already see online available. So today I will be speaking about TMDC nanophotonics for strong light matter coupling. Actually, most of the talk really will be about TMDC nanophotonics and strong coupling, but it will not be limited just to that. In a few occasions, I will do some, let's say, some other topics will be also introduced. So let me start with first acknowledging the people who actually did this work. Mostly, I would like to acknowledge the present and former group members of my group who contributed to the experiments that I'm going to show today. Also, specifically, I would like to mention our collaborators in the electron energy loss spectroscopy project, Andy Yankovic, Eva Olsson from Chalmers, and Mathieu Kocek from Paris Sud. And also a project on time-dependent DFT polaritonics together with Thomas Rossi, Paul Erhardt, and Tomasz Antosiewicz. I would also like to acknowledge the funding agencies and specifically also mention the 2D Tech initiative that we have launched at Chalmers recently. So it's quite a big initiative on 2D materials. This goes not just into my group, but it's a bigger initiative. And we are hiring some postdocs there and even PhD students, so this could be interesting. Finally, I would even like to mention this company's Menatech. So actually part of the stuff which I will be discussing today is even commercially available. And if you're interested in that, you could just go and visit this website. So with this, let me switch to the main topic of our discussion today. And of course, it will be kind of about strong coupling, but I would like to go a little bit maybe more specific here and just mention to you that in the first parts, like part 1 and part 2 of my talk today, I will discuss this generic picture of cavity emitter strong coupling, all right? So in the first part of the talk, actually the cavity will be a plasmonic cavity. And then in the second part, it will be a more extended Fabry-Perot cavity. And then anyway, both of these scenarios will be covered kind of by the cavity emitter strong coupling concept. But that's not only a part which I will discuss. Another thing which I will discuss, and this is a little more on the 2D materials side. Here in part 3, I will discuss actually a concept of self-hybridization or cavity-free concept. So in this kind of scenario, you don't really need an external cavity, a separate cavity and separate emitter. In this case, both the cavity and the emitter, they are confined by the same material. This could be 2D material, that could be some other materials. And then the optical modes confined by this material are then interacting with, let's say, resonances, material resonances such as excitons or phonons in the same system and hybridize together forming polaritons. All right. So we are now quite deep into this polaritonic chemistry webinars, and probably a lot of our listeners already super familiar with this topic of light matter interaction in this simplified 2x2 Hamiltonian picture. So I will not bother you too much with these details. The only thing I would like to mention here is that upon diagonalization of this simplified Hamiltonian, in the assumption of the zero determinant between cavity and emitter, you obtain this Rabi splitting, which looks like this. And in fact, you form polaritonic bands beyond this point over here, exceptional point. And you can see here that in order to form that, your coupling strength G has to be greater than the losses. But in fact, you see that here that there is a minus sign over here, which means that you can actually compromise the losses by making them exactly the same in the cavity and the emitter part. And then it turns out that getting this kind of polaritonic splitting is actually not such a big deal, right? So if you if you know about that trick, usually what you're trying to do is to compromise this part over here. So how to increase the light matter coupling in practice? Well, let's take a look at this simple equation, which tells us the ratio between the coupling strengths and the cavity loss, for example, because usually we're working in the regime of bad cavity. And then this guy is proportional to the square root of n times the dipole moment of the emitter. And this is the part which is related to the emitter. And then on the resonator side, you have two other parameters which are important. That is the quality factor and the mode volume. So then to reach the strong coupling and to increase it, the light matter coupling in practice, what you could do, you could increase the quality factor. And this is what photonics does, right? So you increase the quality factor here, it is easier to reach the strong coupling regime. Another possibility would be to reduce the mode volume, and this is where plasmonic field is. So you can focus the light very well beyond the diffraction limit. You decrease this parameter over here, and it's easier to get into strong coupling regime. And finally, on the emitter side, what you could do is you need to use a material with strong oscillator strengths. And in my talk, I will be quite many times referring to TMDCs because they have strong dipole moments, they have strong exciton bands in this kind of structures, like for example, here shown molybdenum sulfide. And in fact, we want to explore the strong exciton bands for the purposes of strong light matter interaction. All right, so let me go further and start with part one. I remind you that in part one, we will discuss strong coupling on the single plasmonic nanoparticles. So actually here, I need to probably make a comment that the majority of stuff that I'm going to talk about today is going to be experimental. There is just a few theoretical concepts discussed today, and this is one of them. And actually, let me briefly try to motivate this for you. So actually, when we're speaking about polaritons, and in particular about polaritonic chemistry, then we all know by now that polaritons are sort of hybridized modes of light and matter, right? That means that it's somewhat in the middle, right? So in order to treat them properly, you need to treat light and you need to treat matter on equal footings. But that's actually very often a problem, because let's say if you're approaching this problem from the quantum optics side, then you do treat optical part on a rather high level with all your quantum optical Hamiltonians, but the matter side is treated very poorly. In particular, sometimes the two-level approximation is made and there is nothing else beyond that, right? Also, similarly to that, classical electromagnetism, let's say with Maxwell's equations and so on, you very often use the approach of the electric function, for example, and that, although can predict your optical modes rather well, but again, the matter side is somewhat complicated. And then you can do the reversal problem, right? You can treat matter on a very good footings, let's say like what density functional theory does or other type of atomistic methods. When you treat matter part very well, let's say with little approximations, but your optics part or your optical modes are then sort of problematic. So in order to kind of try to avoid both of these problems and at the same time to make as little as possible approximations, we decided to actually simulate a relatively small system. And this is the compromise here, right? Because, you know, in order to have, let's say, explicit treatment of the cavity, your cavity needs to be small. So in our case here, the cavity which was supporting plasmonic particles was actually calculated from first principles, and that contained only 201 aluminum atoms. So it turns out that such a cluster like this shown here can support the plasmon, and it can support this collective plasmon mode here at about 7.5 electron volts, right? Next step is to find an emitter which would be overlapping nicely with that plasmon mode. And surprisingly enough, maybe not so surprisingly, but you know, a simple molecule of benzene turns out to have the resonance also in that range. And what we do next, we mix up benzene and aluminum nanoparticle plasmons into this kind of structure. And this is the coupled structure in which we see Rabi splitting. We see this kind of polaritonic bands. But because we use the first principles approach with time-dependent DFT, we can get also polaritonic orbitals, and they look like this. You know, we have an aluminum particle over here and two benzene molecules over here. So it's really a sort of beautiful what we obtain here, because it provides much more details about the system. You see, for example, the way these polaritonic orbitals behave. They, for example, follow the symmetry of the polariton. One of them is symmetric, one of them is anti-symmetric, but that's not only it. Take a look over here, for example. There is a lot of details in here. And although this is sort of a compromise in terms of number of atoms and so on, this particular method is limited to like not so big systems, but we think it could, in principle, provide some nice insights into polaritonic chemistry in the strong coupling regime. So this paper is now published, and you can take a look at that following this reference over here. So what else we did in this study, we actually looked at the dependence of the obtained signal on the number of emitters, so number of benzene molecules, trying to look for collective effects, and also on the particle size effect. So what you can see here is that we went all the way from a single benzene molecule up to 8 benzene molecules, and we have constantly increased the Rabi splitting obtained in this system over here. And we also increased the number of atoms in aluminum cluster, going all the way from 201 atoms to 586 and to 1289. And the result was the following. When you fit all your data, the coupling strengths versus the square root of number of molecules, you actually see that, interestingly enough, the standard Tavis-Cummings result that the coupling strengths in the collective regime is just this, proportional to the square root of n, holds pretty well for all of these situations. And maybe another important thing to mention here is that the highest coupling strength actually was obtained for the smallest aluminum cluster. And as you make the cluster bigger and bigger and bigger, there is less and less and less of coupling. Okay, so this is interesting. This is kind of really the result which perhaps can be useful for polaritonic chemistry in the future, because we can get out polaritonic orbitals out. And actually what we're working now on continuing in this direction and trying to see further results here, going, for example, even to stronger coupling strengths and so on. So also, again, I would like to remind you that in this talk, I want to focus more maybe on the unpublished stuff. So other things which are published at the moment will be just briefly mentioned. So on this slide, I summarize our activities on molecule-plasmon interactions. And in this case, this PRL paper from 2015, already a really long time ago, we had an individual silver triangles here coupled to J aggregates, and at room temperature, we could reach strong coupling condition on a single particle level. And this is what we actually like to work with, this kind of individual particles synthesized in solution. They are really nice from the point of view of plasmonics, and they are useful for strong coupling. So we went a bit further with this and actually tried to see how this kind of hybrid structure of J aggregates and silver nanoparticle, which results in this nice Rabi splitting, how would that affect the photooxidation of J aggregates in the strong coupling regime? And it turns out that you can actually really slow down the photodegradation of J aggregate in this case. These results are published here. Basically, the long story short, the photooxidation here is essentially governed by this intersystem crossing channel to the triplet state. So when you have the polaritonic states appearing, you can effectively compete with this intersystem crossing by having much faster relaxation rates due to presence of polaritons over here. So you can read more details about this. Actually, the end result is that we see almost 100 times slowdown in photooxidation. Then another result here, published in Nanoletters in 2018, was a single nanoparticle really surrounded densely with J aggregates over here, such that the total coupling here was approaching 500 MeV, so essentially half of electron volts. It's really sort of rather big Rabi splitting that we obtain in this case in the single nanoparticle level. As far as I know, this is probably one of the highest Rabi splittings that you can obtain in this kind of systems. And then finally, recently, last year, we have published a paper in which we looked at the photoluminescence of a strongly coupled systems, again, looking like that. And we have correlated that with dark field scattering from individual plasmonic particle. So this can be read over here. And this is the summary of our molecules. Now let me switch gears a little bit and talk about our activities on TMDC plasmons interactions. So in this case, we actually looked at strong coupling of charged excitons or trions to individual plasmonic particles. And I know that a couple of lectures back, you have already discussed trions. So again, I decided not really to include it and just to briefly mention them over here. What we did in this work, we basically figured out that the standard WS2 monolayer in this case actually supports trions, but they are especially evident when you cool down the system, so you make them more stable then. And turns out that we really can then reach strong coupling with the trions just by cooling our system to 6 kelvins, for example, as you can see here. But in this case, the trions were not really actively controlled apart from temperature. And recently, this year, in this publication in ACS Nano, we actually managed to really control them more actively by applying the bias voltage in this case, and then by controlling the doping levels, we could get different amounts of trions in the system and therefore realize controllable trion exciton plasmon polaritons in the system. Furthermore, we have studied interaction of individual by pyramid in this case with several layers of WSE2. And depending on the number of layers, we actually saw saturation of Rabi splitting occurring in this case. Actually, it's quite interesting structure because here the interaction essentially happens close to that very sharp tip. And maybe another point to mention here, which will be then important for the final part of my talk today, is that we have seen here that saturation of Rabi splitting in this structure occurs at a very small number of layers. It's just 4 layers is enough to saturate the Rabi splitting. And 4 layers of this 2D material is just, in terms of thickness, is on the order of 4 nanometers. So we're really kind of puzzled at first, why would Rabi splitting be saturated by such a small thickness? But then let me a little bit wait with discussing this further. And then finally, we have recently studied this kind of system, again, silver nanoparticle with the TMDC material, but in this case, we probe these plexitons not by light, but by electron beam. And this really allows to look at plexitons with nanometer resolution. So I would like to discuss this point
Professor,
now in more details.
Professor,
Sorry?
we had questions from Zhang Zhedong.
Please.
Okay, now you can talk.
So could you go back to your previous slides, which where you showed us the cavity modified the photooxide reactivity?
This one.
Yeah, the upper right panel. So I'm wondering the reason. I'm wondering the mechanism of why the polariton branches can considerably. I'm sorry. The modified is the photooxide process is because of the change of the spectral density of the bath. Is that the case?
Well, that and not only that. I mean, in principle, there is also polaritonic bands over here. Of course, I guess by the bath you mean the dark states which exist over here still.
Not only because of the bath, and also because of the like, for example, the low vibrational, the low frequency vibrational modes and the solvent motion. Because you know the transition from the upper or either upper or lower polaritons to this T1 state will be well, the transition rate is will of course will depend on the spectral density of the bath. And so if you have but if there is the polariton branches and then the splitting will be changed, and then in that sense the inhomogeneous broadening, inhomogeneous line broadening associated with the bath and bath will be modified. Is that the case?
Yes, I think you can treat it from that point of view. However, in this paper, we didn't really discuss like anything related specifically to this question that you are asking. What we were discussing in particular is just the contribution of the plasmonic damping to the lifetime of the polaritonic states here, and transitions between the dark states, the excitonic reservoir over here, which is a collection of dark states between the polaritonic branches, and how that also is affected by the polaritons. So the bath of the surrounding solvent and so on was not really considered, but the model behind this kind of structure that we had, we actually closely followed the Agranovich and Letinskaya paper from TRB some time ago. So of course, the phonons, they are involved in the processes of, let's say, relaxation from the upper polariton to the exciton bath, and then from exciton bath to the low polariton, and so on. But we didn't include further than that. I mean, it's just essentially a relatively simplified model.
Oh, okay.
Now,
so
you probably cannot exclude other effects which could be relevant, and my guess would be that what you're talking about could also play a role. However, we did not really discuss that.
Okay, yeah. So are you using the second order perturbation theory to calculate the transition rate of, for example, the Fermi-Golden rule in that paper?
Yes, yes. This is exactly
okay.
the Litinsky-Agranovich approach.
Okay, yes. Yeah. Okay. Thank you.
Thanks. All right, can I continue now?
Yeah. Thank you.
All right, so we were discussing the plexitons and nanometer resolution in this case, right? So the questions that we wanted to ask ourselves, that is it actually possible to visualize polaritons on a nanoscale? And the technique that we decided to employ in order to study that process was electron energy loss spectroscopy, or EELS for short. So this was done in collaboration with Andy Yankovic, Eva Olsen, and Matija Kocek here. And what we did here is, at first, we took a look at our individual plasmonic structures. And actually, at a closer look in the high-resolution TEM microscope, we see that the order of atoms here is really, really nice. In fact, all these structures that we synthesize in solution, their quality is really, really high in terms of plasmonics. So their plasmonic loss is relatively small. I mean, there is no like extra damping there. So for strong coupling scenario, this is actually very, very nice scenario. And then what we did experimentally, we in fact could fabricate, first of all, this kind of structures on TMDC, and then we could measure optical signal and EELS signal originating from individual plexitons. And what we can then do, we could correlate between optical and EELS signal, and we could see Rabi splitting appearing both in EELS and in dark field scattering spectroscopy. Moreover, we also got the anti-crossing in EELS signal for many different particles here with slightly different sizes. So sizes in plasmonics of this kind of structures determine the resonance position of the plasmon, and then we could control the detuning of the plasmon with respect to exciton, and therefore the compositions of these polaritonic bands. And in the end, we also performed this kind of EELS signal measurements on really tiny structures for which the signal is actually dominated by absorption. So it turns out there is also anti-crossing there. However, these kind of structures are so small that they're not even possible to measure in scattering. So they are really, really tiny. They do not produce much of the scattering signal. However, the Rabi splitting was still there. And this is a good example of really experimental observations of strong coupling phenomena in this kind of tiny structures. Then we also performed theoretical calculations, and basically found a good agreement between our experimentally measured EELS signal and calculated EELS signal between scattering and measured scattering. And we also could then calculate Rabi splitting in other parameters such as extinction, absorption, and so on and so forth. So these results now appeared in this nanoletter publication over here. And maybe one of the most interesting parts that you could do with these plexitons and EELS is that you could visualize plexiton variation on really nanometer scale, which is hard to obtain using other methods. For example, in this structure that you can see here, you see that we have measured EELS signal at various corners of this triangle, and we obtain slightly different response over here. In fact, it's even easier to map it out if you take a look at EELS maps at upper polariton energy and then low polariton energy, and you subtract one from another, and then you see that this corner lights up. So we see that actually, despite the fact that this system looks relatively symmetric and seems to be simple at first sight, but when you actually start measuring with EELS with nanometer resolution, it is able to tell you much more insights on a nanoscale about this kind of plexiton systems. So again, you can read in more details in this publication over here. Now, I would like to switch now gears and to go to the second part of my talk, where I will discuss more extended structures like Fabry-Perot cavities. And actually, again, being in this webinar series for so long, you're probably all aware of the fact that when you introduce many emitters in between the two mirrors, you can realize strong coupling in this kind of collective effect. It's really collective effect, right? But the point with collective effect is that, well, you need quite a lot of emitters, but these emitters do not need to be exactly the same, right? In principle, you could imagine this kind of Gedanken experiment in which you would have emitters of type A and emitters of type B. And they could be, for example, spectroscopically indistinguishable, but chemically they could be very different, for example. Still, you would obtain in your reflection spectrum, for example, a similar Rabi splitting to this, right? So these kind of concepts are actually relatively old, I should say. So this kind of, I think one of the first who introduced this concept was again Agranovich, and in his case, they've considered intermixed Frankel and Wannier mode excitons between the mirrors of the cavity, and they have realized this intermixed Frankel-Wannier mode polaritons then. Then similar concepts followed recently. For example, people have studied donor and acceptor pairs inside the cavity, or they looked at co-hybridization with solvent molecules and molecules inside this Fabry-Perot cavity and so on. So what we did in this publication is a little bit in this direction, I should say, but perhaps even a little bit sort of even more different, because in our case, what we mixed up was not just molecules of type A and type B, but actually we introduced here plasmonic particles, and plasmonic particles had a similar resonance as these kind of molecules that you can see here. But the oscillator strengths of plasmonic particles is much higher than molecules, which means that even with a small amount of plasmonic structures, you're able to get the Rabi splitting in this collective kind of effect, very similarly, again, optically to this kind of system. So we call this hierarchical microcavities when we have Fabry-Perot microcavity, then we have plasmonic particles, and then we have the molecules. So the way to realize that experimentally, actually, we started like this. We have fabricated first the nanoparticle lattices inside the Fabry-Perot cavity. Lattices look like this. And then when you look into your reflection spectrum, you see that if you compare a bare Fabry-Perot, which is shown here in black, with the Fabry-Perot now containing the particles inside, you see that particles give you Rabi splitting. And this Rabi splitting is actually dependent on how many particles you have. So on the lattice parameter over here, the more particles you have, the more is the Rabi splitting. And you actually can reach pretty significant values here. For example, we easily could reach a value of about half electron volt Rabi splitting. All right. So what you can then do, you can imagine the following situation. Let us say we produce a two-level, or actually a 2D material like a monolayer WS2 in between these two mirrors, and you get into the polaritonic regime, you get the Rabi splitting, which is not that significant because the oscillator strength of a monolayer is not gigantic. But you do get polaritons here, and you do get, see them in reflection, and you see them also in emission and photoluminescence, and even you see emission through the low polariton. Now, what could happen if we introduce plasmonic particles on top of that? So in this case, you see that the Rabi splitting here is much higher than we had in the case of just bare WS2, but the emission here still occurred through the low polariton. Actually, this is kind of surprising to us. And in fact, you can even ask a question, what would be the limit then? Actually, why this happens? But the emission here really occurs still through the low polariton, which is quite interesting. And this is sort of really the situation in which, or kind of, this is the expected behavior of polaritonic systems. Polaritons usually emit from the low polariton. And this is what is observed in this kind of system. So we further looked at this scenario here, and actually the samples that we get here, they are really nice because you can fabricate your plasmonic nanoparticle array and you can position your 2D material on top. And what you get, and when you sandwich all this in between the mirrors, you actually get a sort of all-in-one experiment here. In the area A, you get the empty cavity and you can measure that. On the area B, you have a cavity filled with just 2D material. On this area, you get the cavity filled with particles only. And in this area, you actually mix in all three. And then you can easily compare all of them and draw your conclusions out. All right, so then we have actually performed this kind of dispersion measurements, both in the reflection and in photoluminescence. And actually, depending on the situation, the empty cavity, the cavity with the 2D material, with cavity with just nanoparticles, and then the final system containing everything, it really behaves in such a way that as you add plasmonic particles, you seemingly increase in the Rabi splitting here, and the emission still occurs through the low polariton state, which means it's actually a kind of interesting concept, right? So you're mixing like very different substances. You're mixing plasmonic structures and you're mixing 2D material, but yet polaritons seem to behave in a proper fashion. So in fact, you can read more details in this publication here. In fact, we actually went even further with this approach, and we decided to check what will actually happen if we introduce even more oscillator strings in the area between the two mirrors. In this case, we have really fabricated plasmonic nanoparticle arrays, in this case rods. And these rods, if they are sufficiently strong and sufficiently densely packed, then you can obtain Rabi splittings here, which could be really, really big in comparison to the resonant frequency. So what you could realize ultra-strong coupling regime in this kind of plasmon microcavity polariton systems. And formally, the ultra-strong coupling regime is reached when G over omega is exceeding 0.1. So in this case, as you know, if you want to treat such an ultra-strong coupling scenario with the quantum optical Hamiltonian, what you could do, you cannot get rid of the fast rotating terms, and you also need to include the A squared term. And in fact, we have used this specific form of the interaction Hamiltonian, which closely followed the Hopfield Hamiltonian in the Coulomb gauge formulation. All right. So when we then went to the experimental—
Excuse me, Professor?
Yes.
Sorry to interrupt. We have two questions. First, from Howell.
Oh,
Yes.
hi, Timur. I have a quick question. When you were showing your surface lattice resonances inside of the cavity with the 2D material, how does the Rabi splitting compare with just having surface lattice resonances and the 2D material versus inside?
Yes. So actually, thanks for the question. I didn't really stop on this in detail. The point is, we didn't really have surface lattice resonances here. We actually had them, but they were quite far detuned from the plasmon resonance of individual particle. As you can see, the separation distance between the particles is rather short, so all the lattice resonances appear relatively far away, so they are detuned. So we can't really, I mean, there is no surface lattice mode. I mean, it is there, but it is outside of our spectral range of detection.
Again, this is because there's a high concentration of the
yes,
distance.
Exactly.
But so is it really worth? So do you get anything interesting by by having all the situations inside of the cavity, like the SLRs inside of the cavity?
Oh, this is a very good question. I think probably you will get a lot of interesting stuff there, but we sort of, for us, we wanted to try to keep the system on a relatively simple level. So I would say I would expect something interesting to happen, but we decided, at least at this point, to keep it, let's say, simple. So we just tried to couple to individual plasmon resonance of the nanoparticle and leave surface lattice modes for a while out of the consideration.
Okay, thank you.
Yes.
We have another question from a row Templar. You may talk now.
All right. Yeah, actually, the question I wanted to ask is very similar to what Joel asked, but kind of the opposite. I was wondering if you consider this system but remove the TMD, would you see polariton, like Rabi splitting, emerging from the interaction between the cavity and the plasmonic array? And if
Oh
so,
yeah,
what
but
would
this
be
is
the
exactly
magnitude?
what this slide is describing.
Mm-hmm.
Yeah. The only sort of problem with this kind of situation is that there is no emitter, so it is hard to observe photoluminescence out from this system. And photoluminescence is kind of important quantity still because we would like to measure, you know, emission from this polaritonic system and then see whether it occurs, for example, through low
Okay, I
polarity
see.
or through some other branch.
So that is the that is sort of the smoking gun that the TMD is actually involved.
Yes.
Okay.
Yes, this is the way to get out the signal. Out.
Right.
Otherwise,
Okay.
the only observable would be just reflection.
Thank you.
Yes.
And, we have one last question from Jamie Gomes Rivas. You may unmute yourself and talk now, Jamie.
Yes, can you hear me?
Yes.
Yeah, no problem.
Yeah, yeah, thank you very much. Yeah, no, so I was also following on the question of Joel. So conceptually, I mean, you have this this cavity, right, which is a photonic mode, and then it couples to the localized plasmon resonance on the individual nanoparticles. I mean, this is a very similar concept than the SLRs, in which you have a diffraction in the plane of the array, which is also a photonic mode, so with coupled to the localized resonance on the individual particles. So my question here will be, I mean, here I understand you don't use SLRs in this approach, but what is then the advantage compared to a simple SLR in which you have, probably even a simpler system with an open cavity, right, and it's only diffraction. So can you elaborate a bit more on the advantage of having this geometry compared to an SLRs?
Mm-hmm. Well, I mean, in principle, you're right, Jaime. It's sort of very similar situation, with the only difference is that by Fabry-Perot, we introduce a little bit different mode here. And this mode is then, well, it is easy to control it, and it is also different from the point of view of the way of how you observe the system and how you excite the system. But conceptually, I sort of agree that it is not really.
I guess, I guess that here you can also close back these particles because you don't need to place that at a well-defined distance, which is given by diffraction. So you may also gain maybe in packing density, so achieve probably a higher coupling strength.
This goes back to my, so this goes back to the question of Joel. And indeed, actually, we did not consider SLR itself because we really tuned it outside of the interest here. So as you can see, the density is indeed very, very high. And in this case, well, you could say on one hand side that we could improve the density and therefore the total oscillator strengths of the system, probably beyond the typical scenario of SLR. But I'm not really convinced that, let's say, the concept as such is totally different. So I would say it's, indeed very similar concepts. Some of them, well, it might have an advantage even to just work with the SLR modes, perhaps. In some
thank you very much.
Yes.
Thank you.
All right. So there one more question from Juan Paris. You may unmute yourself and talk.
Yeah, just to finish with the questions about this SLR system. I imagine there is an angle at which you definitely have resonance between the these SLR modes and the cavity frequency, right? Are you measuring like a zero angle, the emission at zero angle, at k equals 0, or?
So this is the picture which answers your question. We have studied this in the dispersion within some angle that our microscope objective allowed us to collect. And within this range, let's say between sinus of the angle between -0.6 and 0.6, we didn't really see extra features appearing.
Okay, thank you very much.
Mm-hmm. But yes, of course, there should be dispersion involved.
Thank you, Professor. You can continue.
Right. So actually, there was a question already. What would be if we remove the TMDC material from the situation or from the problem? And in fact, we have done it here. So we really have increased the density of plasmonic particles so much that we could reach the ultra-strong coupling regime in this case. The total coupling strength increased in comparison to the resonance frequency above value of 0.1. And you can read about this here. So experimentally, this was realized like that. We have fabricated by electron beam lithography a dense array of plasmonic nanorods inside the Fabry-Perot resonator. And here, because of the fact that plasmonic nanorods are anisotropic in plane, then along the long axis of the plasmons, we could create the Rabi splitting, which was rather big in comparison to the resonance frequency of the nanorods themselves and the Fabry-Perot cavity itself. So we do reach the ultra-strong coupling regime. But if we polarize our light perpendicular to the plasmonic nanorods, then we can switch it off. And maybe another interesting point that we have seen here is actually there was a really extreme line narrowing of the plasmonic nanorod array inside this cavity. If you compare the full width half maximum of the polaritonic band and the original nanorods, it's much, much narrower, about 10 times more narrow. And if you actually look here at the FTDT calculation of a similar structure, you do really reproduce this kind of behavior. The lower polariton and even the upper polariton, they are much, much more narrow than plasmonic nanoparticle array. And this plasmonic nanoparticle array, I mean in free space. So this is kind of interesting, I think, because this allows us to create a simple model platform for studying ultra-strong coupling regime. And this kind of narrowing is just one example of where this could be potentially interesting and useful. In fact, we have recently sort of tried to merge this approach with this approach in the mid-IR part of the spectrum to realize sort of vibrational polaritons in this kind of system of plasmonic nanorods and molecules. These results, however, I will not show today. So just from the ultra-strong coupling point of view, what is interesting in this system is that, well, once you reach the ultra-strong coupling, because of the presence of the fast rotating terms, you do get the photonic component in the ground state. And this could be a way to influence the ground state energy also. For example, if you just solve the Hopfield Hamiltonian with the fast rotating terms and with the A-squared term, you do see that there is a non-negligible change in the ground state energy. For example, if you compare the 0-point energy of the uncoupled system, which would be h bar over 2 omega cavity plus omega plasmon, and that of the coupled system, it turns out that they are not exactly the same. And in fact, the difference could be calculated analytically, and it turns out to be about g squared over 2 omega. So in case you are reaching the ultra-strong coupling regime, this situation might not be small. So there could be some interesting corrections to the ground state energy here. And then the question is, you know, what one could do in order to observe these kind of corrections. Maybe this could be actually interesting for something that I will show you now, namely Casimir type of physics. So actually here, let me now introduce this concept. And this is unpublished results here. So the question is, can we actually prepare cavities like that when you have two mirrors and some media in between in a simpler way than in the clean room? For example, could we maybe make it in a self-assembled manner? And it turns out that yes, actually, if we just consider the two gold nanoflakes freely floating in solution, and this kind of gold nanoflakes can be easily synthesized, you can create an equilibrium here by balancing between attractive Casimir force, which acts in between these two mirrors of gold flakes, and repulsive electrostatic force. So this is extremely similar to the DLVO potential and stability of colloidal structures, with the only difference that this now goes to the gold nanoflakes. So actually, it turned out that this kind of gold nanoflake can be indeed synthesized, and you can see it here. So what you can see here is the bottom mirror and the top mirror organized in a self-assembled microcavity manner inside water solution at room temperature. What you could see is that they diffuse with respect to each other, but they actually form a, let me run it away again. So they actually form a stable dimer. And interestingly enough, the equilibrium distance between top and bottom flake here is such that the resonance actually appears in the visible range. And when we measure the dispersion of that resonance, it looks like a regular parabolic dispersion. In fact, this kind of cavities are really easy to make. In fact, you don't need to do anything. You just mix them in solution, and once they find each other, they self-assemble and they create this kind of dimers. And then, interestingly enough, you can actively tune them, and you also can see that this kind of structures are stable both horizontally and vertically. So we have observed them actually for weeks without modifying of the resonant position, which is a nice platform, right? So it could be interesting if this platform could be useful for polaritonics. So the most trivial type of polaritons which could be realized in this kind of structure is a trimer. So actually you could imagine that there is a flake number 1, flake number 2, and flake number 3. This can also happen. They form this kind of stacks. And when you measure the reflection spectrum of such a stack, you see that in comparison to dimer, which shows just one resonance, here you see a pair of resonances in the trimers. And in fact, the separation between these resonances, in some sense, can be thought of a sort of an analog of Rabi splitting. So the way to think about this, you can imagine that the middle mirror here is semi-transparent. And as you make it, as you tune it from being or like non-transparent to fully transparent, by, for example, playing with its thickness, you could see that you can control the separation between these two modes which are formed, and they really go all the way up to here. When you have no mirror or fully transparent mirror, you recover this as being the first order Fabry-Perot mode, and this is the second order Fabry-Perot mode. Otherwise, you see this kind of splitting, and this splitting really can kind of be thought as a separation between a symmetric and anti-symmetric combination of the cavity modes inside these two half cavity compartments. So this is in principle a platform which could be used for self-assembled polaritons. The question is, can we go beyond that and realize something more interesting than just positioning of the semi-transparent mirror here? And the answer is also yes. So what we can do here, in this situation, we introduce the 2D material in between the floating mirror and the bottom mirror, and we get into the strong coupling regime between the cavity mode and the 2D material over here. And then we can modulate it with the laser, with a chopped laser light. So if we do this with the bare Fabry-Perot cavity, we see this kind of nice oscillations. Yeah, so we can tune the position of the of the mirror vertically, and therefore affect the resonance position. But if we now tune in the similar way the coupled system of Fabry-Perot and WS2, in this case, we can actually really tune now the polaritonic system, and we can tune it so much that we can, in fact, tune it out of the strong coupling regime. So this is an interesting concept in which we can really, play with polaritonics. We can get it in an easy self-assembled manner, and we can then also actively tune it, for example, by laser, or for example, by changing the salt concentration in the solution, and so on and so forth. We really think that this kind of approach could be extremely useful for polaritonics in general, and in particular, perhaps also for polaritonic chemistry, because this concept allows us to easily compare between, let's say, the situation without the cavity, and then we bring in the cavity by just positioning the top mirror easily on top. So, was there a question or something? Okay.
Yeah, there's a question from Zhang Zhedong, and you can unmute yourself.
Okay, can you hear me?
Yeah, no
yes.
problem.
Oh, okay, thanks. So I'm wondering if the self-assembled polaritons you mentioned here is something analogous to the lasing process. For example, in a laser, you put a continuous pump to drive the system to far from equilibrium regime, and then in the meantime, you have the nonlinearity, and which will give you the narrow linewidth, which that used to be one of the prominent nature of the laser. So is this a self-assembled polaritons look similar to that process?
Yeah, I'm not sure exactly what I mean by that, but the self-assembly here, as I showed, for example, in this graph, it happens without any laser. It happens just in the dark, for example, and we use very low light intensity just to follow the reflection from these kind of particles in solution. So they are formed in a self-assembled manner, really, as we think, just as a result of Casimir attraction and electrostatic repulsion here, which stabilize your system around some equilibrium distance, which luckily enough turns out to be in line with the resonance in the visible range. However, to modulate that system actively, just to modulate, which means, just essentially exert a pressure, light pressure on top of this movable mirror, because this movable mirror is in water solution. We use the laser, and that's the only time we use the laser, all right? Otherwise, there is no laser involved. Just by using this laser and modulating its intensity, we can sort of exert the pressure on the movable flake, and then remove this pressure, and then again exert it, and so on. And you see this kind of modulation can be easily then obtained.
Okay, I see. Yeah, and so what is the role of the nonlinearity in this scheme?
Well, in this scheme, the point is that when you have the 2D material here, and you have a movable mirror on top, by applying this modulation signal, you could actively tune the resonance of the Fabry-Perot microcavity with respect to the resonance of the material. And you can actually tune it much that you can detune it extremely far away from each other, such that the new polaritonic bands, they stop being polaritonic. You can essentially tune it so far away that your delta or your detuning can be significantly bigger than your coupling strength. And in that case, you can sort of switch off the strong coupling regime then. You see?
Yeah, actually, I mean, what is the role of the A squared term, as you mentioned before? Is that related?
Okay, in this case, we are not in the ultra strong coupling regime. There is no A squared term.
Okay, I see. Yeah, okay, thank you.
Yes.
Thank you. There's another question from Wei. You can unmute yourself and.
Hey, Timur, you already talked about this a little bit, but can you actually actively control the distance between the two self-assembled mirrors and then make them, really far detuned from the visible regime into near IR or mid IR? Or they would work near the visible regime?
Yes, we in principle can.
Like, may I ask
a short answer. I mean, if you want a longer answer, we probably need to discuss it kind of separately, I would say. I should say in this kind of structure, we did aim at the visible range, but it turns out there is no principal limitation on that. So we can make cavities much more compact than we are making them here, but we can also make them much less compact. So this is possible. Maybe one limitation that we only have here, sorry, I switched in the wrong direction. The size, the lateral size of the flakes that we have synthesized, they are on the order of few microns. So maybe 5 to 10 microns maximum. So, well, what we have not tested so far is, what would happen if we detune them extremely far away, like really far away.
Oh, I see. I see. Thank you.
But like in the mid-IR should be possible.
That's very interesting. Thank you.
Mm-hmm. Yes.
Okay, thank you, Professor. There's one more question from Matthew. Matt, you can talk now.
Can you talk about the effect of the solvent on the distance between the mirrors? In other words, can you like tune the solvent to tune the distance?
Thank you for the question. So in fact, this graph shows this kind of effect that you're asking about. So physically speaking, well, in our case, it was all the time the water. So I'm not sure what do you mean by solvent, like switching water to something else.
Oh yeah, exactly, like some alcohol or something.
So,
yeah,
but in our case, what we did, we actually played with the salt concentration inside the solvent. And the salt concentration in turn determines your Debye-Huckel screening length and therefore the equilibrium position of your mirrors with respect to each other. So just by replacing the amount or like controlling the amount of salt in the solution, you can control the equilibrium position between the mirrors. But if you also switch from water to something else, of course, this kind of equilibrium between the attraction and repulsion would be different. This is like the simple answer perhaps to your question. How exactly different it will be will depend on your solvent and the salt concentrations and so on.
Okay, thank you.
Surface charges, screening, this kind of parameters are important.
Thank you so much.
All right.
Okay, thank you, Professor. You may proceed.
Okay, where are we? Yes, so we have discussed this kind of self-assembled polaritons, which can be modulated actively by a tunable laser here. Now, let me now switch to the final part of my talk, which will be more focused on self-coupling to itself. So actually, the way we got there was by looking at comparison between monolayer and multi-layers of TMDC structures. So it's very well known by now that monolayers of TMDCs have very strong oscillator strengths, direct band gap, and so on. They're highly useful for polaritonics, and you can realize various kinds of polaritons with them in very different structures. But it turns out that multi-layer systems are also quite interesting, and it has been shown that you can get strong coupling with these multi-layers as well. So in our case here, what really sort of made us interested in this is that we saw in this paper that there was a very fast Rabi oscillation saturation with the number of layers of 2D material. In fact, with 4 layers, it was already fully saturated. And 4 layers is just about 4 nanometers in thickness. So we thought, how could it be that plasmonic fields decay so fast? It's a little bit too fast for plasmonics. And then the answer turned out to be actually in the optical properties of TMDC materials. So these TMDC materials, for example, WS2, turns out to have extremely high refractive index in plane and also extremely anisotropic. So in plane, actually, the refractive index, actually here I show epsilon, but the refractive index is like just square root of that. So the refractive index turns out to be bigger than 4. And that's actually comparable or even bigger than silicon. And you probably know that people are doing a lot of this kind of high index dielectrics in silicon structures and similar type of structures. The question is, can one realize something similar with TMDC materials? And we have started with something relatively simple. Imagine you have a slab of TMDC material with very high background refractive index. Let's say 4 it is the index, right? And then you would then create a Fabry-Perot standing wave in this kind of slab. It would be almost like a Fabry-Perot, not extremely good Fabry-Perot, but still a Fabry-Perot, right? And then simply by playing with the thickness of that slab, you could tune that Fabry-Perot resonance to overlap with the exciton. And once you do that, you can actually self-hybridize your exciton mode to your cavity mode and to obtain this kind of Rabi-like looking splitting. So you would create a polariton without any cavity because the cavity is fully made up of the material itself, right? So we went to the lab and tested this concept. First, we started playing with the thin flakes of TMDC material, something on the order of 10 nanometers, 10, 20 nanometers. And in all cases, when we looked at dispersion, we didn't see anything except for the flat exciton bands, as it should be for just excitons. But when we tuned the thickness to the situation when the Fabry-Perot was actually now overlapping with excitons, turned out that we could create this kind of interesting bands with the dispersion looking almost parabolic-like. And really, it looks like upper and lower polarity formation and self-hybridization inside this kind of thicker flakes where Fabry-Perot mode and exciton mode mixes up, and you just recreate, or let's say reestablish, your polaritonic bands. So in this case, it turned out our splitting was on the order of 200 MeV, but the cavity, let's say the cavity was not that great, so it actually turned out we are not really reaching the strong coupling condition here, but we are on the way towards it. So the next question for us was, how could we improve the quality factor of our resonators to get really into strong coupling regime? And that's really where the concept of nanodiscs as nanoantennas came out. So you know, again, that optically resonant dielectric nanostructures, like made of silicon, germanium, gallium arsenide, and other conventional semiconductors, actually support Me modes, dielectric Me resonances, right? And this is well described in this paper in Science, Optically Resonant Dielectric Nanostructures. In fact, if you create disks out of silicon, you also can make dark anapole states due to destructive interference between electrical and toroidal dipoles in the disks, which also is described in this publication here in Nature Communications. So the questions to us was, can we fabricate nanoantennas out of TMDC materials? It turns out that yes. So simply by etching the thick layer of TMDC, we can create nanodiscs of WS2. There is a resistant top which we can get rid of, which I will tell a little bit later about. So these kind of discs then support Me resonances. And this is how they look. So WS2 nanodiscs as Me resonances. In fact, when we look at them, they contain a number of rather complicated modes. And the easiest way to see them out, to map them out, is to look at their dispersion as a function of the radius of the nanoparticle. So in this case, we really can get this anapole dip over here, linearly dispersing with the radius of the particle. And if we plot the field distribution at that point, we obtain very much anapole looking like near field distribution. The next question was then, can we make this anapole state to interact with our A exciton and exchange energy fast enough to form Rabi splitting in the system? And it turns out that yes, numerically, by tuning the anapole to the exciton, we can get this Rabi splitting over here. And experimentally, by making our nanoparticles slightly thinner, we can tune the anapole to the exciton position, and then we recover this very nice anti-crossing over here with the Rabi splitting on the order of 200 MeV again. And then by using the Hamiltonian modeling, we could even observe the fast Rabi oscillations between the states involved in this process, in the process of anapole exciton hybridization. So we really can get this fast Rabi-like oscillations, which can be then considered as evidence of strong coupling in the system. Again, in this system, you don't have any external cavity. Actually, after that, we went even further and looked at more complex systems going from single TMDC nanostructures to arrays of nanostructures. So we have fabricated nanostructured TMDC arrays looking like this. And while working with them, it turned out that this kind of structures can be made and they can support different resonances, and they also can be overlapped with the exciton bands in the material. So we can get interesting hybrids. But maybe another thing, which is maybe not directly related to the topic of our study today, it turned out that if we perform an isotropic wet etching of these kind of structures, that we can then reshape this kind of circular holes over here into hexagonal holes over here. And in fact, these hexagons really follow the crystallographic axis of the 2D material, which was very surprising, but very interesting for us then. So we went even further and we fabricated complicated arrays of these structures. They can be made on large areas. They are very reproducible and simple to make. They work in a wide parameter range. we can form really novel nanostructures out of this, like ultra-thin nanoribbons, for example. So this kind of structure here can be as thin as just a few nanometers because it's extremely controlled etching method. And everything really follows the crystallographic structure. So you can read more details now in this paper. So what even turned out is that the edges of these hexagons are really sort of atomically sharp. And when performing Il's study on the edge, it turned out that we really preserve the excitonic properties here. So just the Il signal a few nanometers away from the interface gave us pronounced A, B, and C excitons, which means that the method is really not affecting the properties of excitons in a bad way. So nothing is ruined there. So then we can tune the resonance position of these polaritonics, of these array structures, again to the resonance position of the exciton, and again can get this kind of self-coupling here with the Rabi splitting of about 200 MeVs. So what I've shown now to you so far, it seems that we really can get this self-hybridization approach in TMDC structures. But is this self-hybridization approach actually limited to MDCs, or can it be realized in other material platforms? And of course, you can realize it in other material platforms. All you need is just strong enough transition. And there are really many materials with strong transition. So in fact, this has been shown already back in 1958 by Hopfield in his famous paper in Physical Review, where he showed essentially treated the resonant materials from the quantum optical point of view and showed the polariton formation there. So what kind of materials could have strong enough transitions? Well, actually it turns out if you just look at water has strong enough absorption in the mid-IR range, right? But if you then look at things like clouds, for example, they contain this kind of water droplets with a radius of about 10 microns. So this kind of water droplets, in fact, support me modes. What if we now mix those me modes in this water droplet with this strong oscillator strength absorption in mid-IR range? It turns out that we will get this vibrational me self-hybridized polaritons in this water droplets. And in fact, this can be even achieved in the ultra-strong coupling regime because the oscillator strength of absorption of water vibrations is actually really strong. So in fact, technically what we did here is we treated the Lorentz media described with this kind of equation with the important parameters being oscillator strength, plasma frequency, the resonance of the corresponding transition. It could be excitonic transition or phononic transition, the corresponding width and the background index. And we then followed the polariton eigenmodes in the complex frequency plane as the roots of the corresponding dispersion relation. So this movie shows this kind of eigenmodes in the complex frequency plane. And when we perform this kind of analysis in bulk polaritons, we can, of course, reproduce the result of Hopfield with weak coupling, strong coupling, and appearance of Rabi splitting here, and even ultra-strong coupling, where we see even stronger Rabi splitting and appearance of the polaritonic gap over here. As we go to more complicated structures, like polaritons in Lorentz slabs, looking like this, or polaritons in cylinders, it turns out that we also can get Rabi splitting both above and below the light line over here, depending on the scenario. So in this case, we used GA aggregates with corresponding oscillator strings. And in this case, we used the perovskite nanowires, and we also got the Rabi splitting in this case. So if we then use the similar approach to water droplets and just tune the radius of the water droplet with respect to the phonon in the water, then we reconstruct this anti-crossing here, all right? And we get even this kind of polaritons in the ultra-strong coupling regime with G over omega being bigger than 0.1 in the vibrational part of the spectrum. So, long story short, polaritons turn out to be everywhere around us, even in clouds. Like every time you look in the sky, you see this small water spheres there, water droplets, and they are automatically me-modes interacting and hybridizing with phonons of the water, and they are producing new polaritons. And we can get those in slabs of materials, in cylinders of materials, in spheres. And it turns out also that the maximum coupling strengths that you can obtain from that material is given just by the parameters of the material, in particular by the oscillator strength. So it turns out that this is sort of a hard limit on the coupling strengths also. You cannot really exceed it by playing with, improving the cavities or whatnot. This doesn't really beat the bulk polariton limit over here. So in fact, if you have a question of whether of using or not using any particular material for strong coupling, you should just calculate this parameter over here. If you're not happy enough with your coupling strengths, that you should abandon that material for your strong coupling reasons. But maybe the most important question that one could ask about this kind of self-hybridized polaritons is, do these polaritonic states actually play any role in polaritonic chemistry? Right, so we are discussing polaritonic chemistry quite a lot, and then in polaritonic chemistry communities usually assume that polaritons needs to be formed in order to affect your chemistry in both excited and ground state realizations. So, but what about these polaritons, right? They are everywhere around us. They are like, in fact, impossible to switch off. They are all the time there in the background. And then, do these polaritonic states play a role? And if yes, then which? And if no, then you can actually ask a question, why? So with this, I would like to conclude my talk and to say that in the first part of today, we have discussed cavities and polaritons in cavities, going all the way from really tiny aluminum nanoparticles containing just 200 atoms and hybridizing with benzene molecules, then to polaritons, plexitons studied with eels, then to ultra-strong coupling with plasmonic nanoparticles, and then to self-assembled and actively modulated polaritons in this kind of nanoflakes. And then the second part, I've discussed cavity-free approach in which you could self-hybridize to forbiperosin slabs. You can self-hybridize to me-modes inside the particle. You can even hybridize in arrays and edges of structures like that. And finally, even water droplets are polaritonic. So I would like to thank again the people who contributed to this work, and thank you for your attention. That's all.
Okay, thanks, Professor Shegai. And we will have some last minutes questions from, this is from Pavi Torma. You may unmute yourself and talk.
Yes, hi. Okay, thank you, Timur, for a wonderful talk. I have a question related to this ultra-strong coupling thing, this nanorods inside the fabric cavity, and you use this typical ultra-strong coupling Hamiltonian with A² terms and so on. I'm wondering, I didn't read the paper, did you derive it from some kind of microscopic starting point? Because if I understood correctly, you are mainly strongly coupling the nanorods to the fabric cavity.
Yes, exactly.
Yeah, and that one, I mean, the Hamiltonian has been originally derived for two-level atom interacting with the field. And now you have a field, this cavity field, interacting with the plasmons of the nanorods, which is rather different object. So I'm wondering whether something changes. For instance, this A² terms comes from when the vector potential couples to the momentum of the electron in the standard description. So is something changing if you have actually a plasmon instead of two-level atom?
Yes, I see. Thank you for the question. So in fact, we actually followed the approach very similar to the Hopfield. So we indeed used just the Hopfield Hamiltonian. In this approach, there are certain limitations. For example, your field must be transverse. So like in this case, for a big Fabry-Perot cavity. And actually, the Hopfield Hamiltonian doesn't really require that your system is a two-level system. In fact, it's just a quantized version of the coupled harmonic oscillator problem. But one important thing which is done there is the point dipole approximation. So this is probably referred to your question, I guess, because it is in a sense that you're kind of assuming that your particle or the material to which you couple, it is much smaller than the wavelength. In case of the plasmonic particles, this might not necessarily hold, you're right. However, we stick to this derivation, which was actually done in one of the papers by Simone De Liberato. So in the parameter ranges that we use for our realization, it seems to be relatively well satisfied. We have not really started from, from the first principles here, deriving the Hamiltonian from scratch.
Mm-hmm. Okay, thank you.
Okay, if there are no more questions, let's thank Professor Shegai again for this wonderful talk. And also I will thank everyone for attending and discussion. For next week, we will have Professor Matthew Pelton from University of Maryland as speaker. The title of his talk would be room temperature strong coupling between plasmonic nanocavities and quantum dots. And here, thanks everyone again for today's talk, and hope to see you all next week. Bye-bye.